Thank you, John, for the very nice introduction. Can you hear me? Can the people out there in Radio Land hear me? I hesitate to begin with a comment that refers to an American radio personality who was said to have a very good radio voice and a very good radio face. So Garrison Keillor, who got into a little trouble about 2 or 3 years ago, had a fictional community called Lake Wobegon, and it was the place where all the women were strong, the men were good looking, and the children were all above average. And it's such an honor to be able to give a lecture here at Lumini and have it videotaped, because now there'll be evidence that I'm the Lake Wobegon professor, the one who makes all the rest of you well above average. Okay, so actually, and let me take just one more minute and thank, let's see, Eric and Laurent in particular, and Mark. Mark asked me a couple of years ago whether I was still doing mathematics, and I guess it's pretty funny that, and then he asked me if I wanted to come to Lumini, and I said, I haven't been here for 30 years. So in 1989, Harold Rosenberg organized a conference here, starring, I think, Misha Gromov, and I forget who else came, but a lot of us were here. I think I was the youngest person there then, unless, is Martin here? Martin? Martin's skipping the talk. Oh, there he is. Were you here in 1989? Were you here in 1989? Okay. So I think I was the youngest person at the conference, and luckily for them, I didn't give a lecture. And just so let me end with this to sort of apologize for being a little bit out of sorts. But Bob Hart, who was my roommate at the time, we all had to room together. It was before any of this infrastructure was built. We all had to share rooms. And Bob Hart, I'm fairly tall. Bob Hart's about 2 meters. I'm about 190. And Bob's a big guy. He actually had a professional basketball contract offered to him when he was an undergraduate. But he went to grad school and was a student of Federer, and actually was one of my postdoctoral mentors in some unofficial capacity. And it was here at Lumini that we, just as John said, we got to know each other. We were roommates. And the first time Bob sat down on the bed in the shared room, we had separate beds, of course. But they were of a style where neither one of us actually fit on the bed, and how many more minutes do I have? I think his knees may have just been at the end of the bed, and my ankles were at the end of the bed. And anyway, when he sat down on the bed, there were these slats that fit very nicely. If you're a woodworker like Martin and I am, you can appreciate. They're sort of like mortise and tenon sort of things, but nothing really joined. They were supposed to be flexible. And Bob was, even though he was very tall and thin, he was a pretty big guy, maybe 150 kilos. And he sat on this thing, and of course, where some part was sitting, it forced the cord into an arc, and eventually the cord length was fixed, but the arc was longer, and out it came. And then the next one went, and then the next one, and like that. All right, well, that was okay in the afternoon, but in the middle of the night, I think I was asleep, and suddenly there was machine gun fire. And it was Bob Hart apparently rolling over and having the same thing happen in the middle of the night. So anyway, so all right, now I have 3 more minutes and then I can really start, right? Because we have a 20-minute break, and you're going to give me that 10 minutes of the story, right? So Bob Hart was a runner at that time. I was too. It sort of doesn't show anymore. But so was Nick Korovar, who by then was one of my main collaborators. I think he did give the talk about stuff we'd been working on back then. And Ivan Sterling, I don't know if any of you know Ivan Sterling. Anybody know Ivan Sterling? So he's quite back then, we were graduate students together, and he was quite the image. He was bigger than Bob Hart, but not as tall. And he had a beard that I've been trying to grow for 30 years, and his beard went down and down and down. People said he resembled Poseidon. My wife says that he resembles Poseidon, okay? Emerging maybe from, well, sort of Venus and Poseidon together, emerging on a half shell from the Calanque. Anyway, we all decided to run to Cassis one day. And this was it was just before the bicentenaire, so it was late June and the first 2 weeks of July in 1989. And we decided to run, because we were there, we had a 2-week session. I think it was on the weekend. We wanted to run to Cassis. And there's a gorge long, I think. There were no Googles, there's no Google then. There was a topographic map, and we studied the map. We just tried to memorize the map and get our directions. And I don't think we took water with us. And we started running, and Bob Hart and Nick turned back, but Ivan and I persisted. And we got pretty far into the gorge, and we started getting thirsty. And we had no idea really where we were. And we sort of imagined what it would be like to immigrate from Lumini to Cassis and be found by the Border Patrol, dried hulls in the desert of the Gorge Long. And so eventually we just gave up, and we seemed too far to go back. We sort of remembered if we climbed over the mountain, we could get back more quickly. And we got up over the top of the mountain, then we came to a cliff face. And we were looking down, and you can see them from here. And luckily, there were these little pitons and chains already fixed there, all ready for us. And I said, oh, great, I've done it. And Ivan, who's this tough guy, he'd been in the US Marine Corps, I learned. And that's why he grew the long beard, because for 3 years, he had a crew cut and had to, yes, sir, kind of business. And then he went completely the other way. So we were climbing, I was climbing down, and he was still up there at the top. And he kind of looked at me with a look of panic when I got to the bottom. Maybe 10, 15 meters you go down. And he said, I can't do it. And I couldn't believe it. So I kind of talked him down, and we made it back okay. But anyway, so here we are. Okay. So I finally got to Cassis last night for the first time in 30 years, thanks to Mark and Marina. So thank you. All right, so let's get started. So I want to talk about some stuff that's, is that okay? Actually, I want to talk about some stuff that mainly is joint with Peng Wang, so I'll say it and I'll try to write it. But I thought I would say a little bit about, well, if you can see this, about sphere aversion, since we had a very nice talk yesterday morning by Alexei. I think I just saw him. There he is. And maybe I'm not sure what we want to do, but I think I need to start it. So this is very short. This was made based on some experiments that Alexei mentioned that actually we began in the early 1990s, these experiments, and decided to make a film. And the film was sort of taken over by John Sullivan, who's a very good visual mathematician. And it's called the Optiverse, the long version of it. And you may have seen this. So this is just available on YouTube. But for those of you who haven't, I just want to advertise this. The idea goes back much earlier. And I just want to, since I once explained kind of in about a 10-second interlude, I guess it was last fall at the Institute, how this came about. So you guys know about the archive, right? So the archive lets you put all your ideas up there now. But back in the old days when I was a beginning student in the early 1980s, people didn't do that. They came to Berkeley and they gave a lecture. So Robert Bryant came to Berkeley, I think in 1982, and gave a lecture on his work about Willmore spheres. And his main result was this quartic differential that lets you see that has to vanish on a Willmore sphere. And from the geometry of that lets you see that a Willmore sphere is actually a conformal compactification, if you like, of a minimal surface in R3 with planar ends. And he gave somewhere in the lecture an example which had a four-ended surface, and you didn't have a picture of it, but you talked about them yesterday. And at the time, I was not really sure if I was going to do geometry or geometric analysis or low-dimensional topology. And I'd been studying with Rob Kirby various things about immersions, and I had taught myself Smail theory, and what was the other thing that was, the new thing was Alan Hatcher's proof of the Smail conjecture, which is not about immersions, but about embeddings. So it's a theorem about the diffeomorphism group of the three-sphere, and one way of understanding it a little more geometrically, it's about the space of embedded two spheres in three space. And what he proved, what Alan Hatcher had proven was, so I'm going to come back to Bryant in a minute. Alan Hatcher had proven that the space of embedded spheres in R3 is contractible. And I thought, well, there should be a good way to do that using a flow. This was 1981, okay? Flows weren't that big back then. And I wanted to do the Willmore flow on it. And of course, you know the problems with that, okay? It doesn't preserve embeddedness, among other things. And once I realized that, then I had other ideas. But I also knew about the homotopy type of the space of immersion. So it's connected, but it has a nontrivial fundamental group, as you pointed out. If you take oriented surfaces, I think maybe that Z2 goes away. I have to think about that extra Z2. But basically turning a sphere inside out, which is what Smail had shown in his thesis 20 years earlier, 25 years earlier than was a very good candidate for an interesting, well, something that I didn't know how to do then and that you and Tristan Riviere have been working on, an interesting way of actually constructing critical points. So Robert Bryant had talked about Willmore spheres, and he said he had this example with energy 4 pi times 4, and there were no examples lower than that. I went up to him, after maybe even raised my hand, as you've seen in the talk, and said, I think I know how to explain that variationally, because there was a theorem which you mentioned, the Banchoff-Max theorem, that any sphere version has to pass through a quadruple point. And it's also known that's a non-trivial, well, relative loop, or if you do it twice, it's a loop in the fundamental group of the space of sphere versions, sphere immersions into R3. And so that was when I first sort of thought, there's some connection between this. That was a long time ago. That was the 80s, and that was how we had that interaction. So this is a video showing the idea that I had in 1982 and put into place to actually, I used the idea I couldn't do the minimax thing. It's still not quite done yet, but but I had the idea that you could use this to actually construct minimal surfaces. And so this video is based by starting with what we call the Moran surface, the Moran minimal surface that Robert Bryant found a family of. I found the symmetric one that we start with, explicit Weierstrass data for it. And then it does a numerical approximation of the Hessian of the Willmore functional, the discretized Willmore functional, and runs it along the most negative gradient direction of that. So at least numerically, we had some idea of what the lowest eigenfunction of the Willmore second variation operator looks like for these things. So let me just show this, and then I'm going to switch to the actual topic, because I'm going to run out. I'm obviously running. It's not going. There it goes. So there's right about, well, I think it does it twice. So this is the full loop, and right about there is the minimal surface. Okay, so that's what you've been doing lots of good analysis on. And there's a whole family of these that have not only, so I'll do it one more time, but this has the property that it actually has twofold symmetry, twofold rotation symmetry throughout the entire loop. And for any positive integer, an integer greater than 2, there's a similar version with that integer fold cyclic symmetry. And those surfaces, the midpoint for that eversion turns out to be at least a critical point for the Willmore energy. Although I guess we don't really know how to prove it using minimax yet. But that was the basis for the films that we made back in the 1990s, which is when this dates from. Okay, so that's what's behind at least some of the stuff that got me interested in Willmore surfaces. Okay, now I'm going to make this black screen and turn to this. Okay. And now I'll switch to light. And it's this middle one? This middle one. Yeah. Good. Okay. Okay, so we're going to look at Willmore stability and rigidity. Okay, and most of this is joint with Peng Wang. I may say some things about, so Peng Wang is, I may say some things about free boundary minimal surfaces, which we've also been thinking about, and also with, maybe that's supposed to be with Peter McGrath, who didn't show up. I don't know what happened to Peter McGrath, and Ilana, who didn't show up, Ilana Fraser. And if I have time, which I doubt I'll have, I may come back and say some things about minimal surfaces with planar ends. Last week I was in Darmstadt and had a good chance to kind of think about it some and have some sharpening of results that Alexei and that Elena Mader-Baumdicker and Jonas Hirsch have done. So we'll see how that works out. Okay, so I want to start with just a couple of elementary observations. And of course, in Rn, if I think of the n sphere in Rn plus 1 and take a surface, and I'll be thinking mainly of embedded surfaces, and I may just write that without writing down the name of the embedding or immersion. If I have a surface in here, then so that's my n sphere. Okay, and then my surface I'll just depict like so. Here's my surface. Okay, if I think of the surface as sitting in Rn plus 1, then it has a mean curvature vector, and its Willmore integral thought of as sitting in Rn plus 1 is, of course, the integral of the square length of that, the area, which is how to denote that. But if you simply decompose using the Pythagorean theorem, I always like to use the Pythagorean theorem, into the part that points right into the center of the sphere, okay, the mean curvature has two parts, the part that points right into the center and a part that's on the surface. So this is the mean curvature. So I'll think of this as the mean curvature vector in Rn plus 1. I'll just write h for the part there. So the mean curvature would be, then I can also think of this as by the Pythagorean theorem. It's gone. Okay, so it's the, and you can think of this as just the area. Of course, this is the area of sigma plus, and then variationally, since that's what this workshop is about, variationally, right? This is the, well, this is twice the, h is twice the, so h, if you like, the mean curvature vector in Sn is twice up to a sign, so plus or minus. The first variation, which I just want to show a little calculation. Maybe I won't even do it all, that I also did back in the 1980s, and it's sort of an interesting little calculation, which somebody should make rigorous. But I can think of maybe with a minus sign, and actually it's not that, it's that, of course. No one objected, and maybe there's a minus sign there, okay? Depending on how you orient stuff. If the mean curvature is pointing inward on a sphere, then that's the right formula. So this is what? So this is plus a quarter a dot squared. Well, let me write it this way to make it look more like where I'm taking an L2 inner product, okay? So this is an L2 inner product. Okay, so so variationally, you should think of the Willmore functional, or you can think of the Willmore functional of a surface in Sn as the area plus this extra term. And so if you then compute W dot and W dot dot, I think I won't do both because I can't. I've been teaching linear algebra for the last few years. Calculus is not on my list, so I'll let you do the calculus. But you get something like this if I've done this right. Oh, and so in general you get something that involves the third variation. So you get this. You'll get stuff that involves the third variation here. So do I have to do this? I'm not going to do this. So you'll do this calculus. So by calculus, or whatever it's called, analysis 1. Okay. Well, what you'll get for this, if you assume you're at a minimal surface, so at a critical point. So at a critical point, so at a minimal surface, we have that A dot equals 0, because the mean curvature is 0, minimal surface sigma in Sn. And what you find is that the second variation of the Willmore functional is I think it's a half, and then A dot dot composed with, if you like, A dot dot plus 2, okay, if you work that out. Okay. Something formally looks like that, okay? So pause for a minute, let me get my whistle. Okay, and so what do I really mean by that? Well, A dot dot is the Jacobi operator for area. So let's see how this works. So in the sphere, so A dot dot up to a sign. So I might need to use minus signs here. So it's something like maybe it's minus. Think of minus L if you like. So minus. Well, I take sections of the normal bundle. So this is the Laplacian actually on the normal bundle, okay, on sections. So in the case of the 3-sphere, I can think of this, the normal sections as functions. Since I'm an embedded surface, functions times some unit normal. In higher codimension, I really need the Laplacian on the normal bundle. So this is. Okay, and then there are two more terms. Okay, so one of the terms is actually pretty easy to understand. It's the Ricci term, so there's a Ricci kind of term there, and then there's a term which maybe I'll call A, okay, which is a second fundamental form term. Okay, in codimension 1, in the 3-sphere. Well, actually, in every dimension, this number is just 2. It's basically the Ricci curvature on the tangent plane of the surface. Okay, so this operator has the following form. It's 2, and this would be the square of the second fundamental form's length. Okay, in codimension 1, it's a little more complicated in higher codimension, but it's a symmetric endomorphism of the normal bundle. It's essentially made from the second fundamental form, thought of as if you like, thought of as the shape operator. So so I'll just write it A again. Okay, so this is the area-Jacobi operator, second variation operator, area-Jacobi. Okay, and so what this tells us is that if I write this a little more, right, that we have, maybe I'll call this L, okay. So operator L, okay. So L plus 2, and we're interested in the stability of this operator, okay. So this is the, maybe I'll call this J, okay. So this is, I'll write this. So so for a minimal surface in S3, the Willmore Jacobi operator, so this is the Willmore Jacobi operator. And I think this is, in your talk, Alexei, you actually did some analog of this, and sort of for a minimal surface, if you choose the right kinds of sections, you have to be careful what happens at infinity. You get something like this. Again, it's like the square, it's roughly the square plus a lower order term. Okay, so that's the idea for the case where you have a minimal surface, then the operator becomes very simple. But for a non-minimal surface, you end up with third variation of area terms. And I'm sure some people have calculated that, maybe you have yourself. But not many people know about the third variation. So project 1 for everybody is to understand the third variation of area. Okay? Okay. So what does this say? So let's look at what this says about the So we want to understand the spectrum of this operator. So this is a self-adjoint operator. It's the composition of two self-adjoint operators of a second order, so it's a fourth order self-adjoint operator. It starts out with the Laplacian squared, as you might expect. And on a compact surface sigma, it therefore has a discrete spectrum. And since it's in fact it's not a positive spectrum, but it sort of goes to plus infinity also. In fact, what's the relation between these? So let me write. So how about the spectrum? What's the spectrum just look like qualitatively? Well, this involves. We did calculus, now we're going to go back to analytic geometry. So we're going backwards in our education. So let me write alpha for the spectrum of L. And maybe, let's see, I think I'll call this omega for the spectrum of J. Right, so the relevant parabola to draw here. Let's see. So if alpha is 0, or if alpha is -2, right? This thing has roots there, and it's a parabola that goes upward, as we said. Okay. Right. Okay. So what's going on here? So of course these are area-Jacobi fields, right? So these are the area-Jacobi fields. And in particular, any rotation of the end sphere gives rise to something like that. So in general, we're going to get a large eigenspace corresponding to alpha equals 0, but it's also a Jacobi field, of course, for Willmore, okay, for W. These other guys here, okay, arise from, so this includes, rotations, well, whatever, SO n+1, okay. The eigenvalue -2 for the area-Jacobi operator, well, it turns out there are many interesting ones in there, but the ones that are always in there come from what I'll call the centered dilation. So in the sphere, if I take say some point and its antipodal point, there's a Möbius transformation of the sphere that fixes those 2 points and pushes all the parallel spheres between those down, okay? And in fact, the centered dilation you could think of as its action on the sphere, its velocity field, is gotten simply by taking a constant vector field on Rn+1 and tangentially projecting it to the sphere. And then if you look at its normal projection to the projection to the normal bundle, you get a normal variation of the surface, and those all end up here. So here we end up with basically Möbius or Möbius Sn mod SO n+1. Okay. So that's actually an n plus. This is an n plus. This is essentially the same as the hyperbolic n+1 space. There's an n+1 parameter family of those in general. There's some degenerate cases like an equator. Equator is invariant under a 3-parameter family of such things that fix that send the equator to itself, the equatorial, or a totally geodesic 2-sphere inside the sphere. So there's some exceptional cases where it's lower dimension, but basically have that dimension. So both of these eigenvalues occur with multiplicity and fairly large multiplicity as long as the surface is picked generically. Okay, and so the question about this picture means so sigma is Willmore stable if and only if the spectrum of J is positive, which is if and only if the spectrum So this is for a minimal surface in Sn, if and only if the spectrum of L doesn't meet the interior of that interval, okay? So if I had eigenvalues in here, all right, they would give rise to negative eigenvalues, negative omega eigenvalues, right? So this is, okay? Clear enough, I hope. Okay, so what are some examples of Willmore stable minimal surfaces and non-ones? This one I don't need a machine for, right? So, okay, so that's supposed to be a picture of the domain of a Willmore stable minimal surface. We know now. I mean, this. So by the way, this I should give some credit here too. So this calculation was suggested by a paper from 1978 by Joel Weiner. Okay, and I think I first did this little calculation back in about 1982 or 83. Just to check his thing. So he actually carefully does some of this for any codimension, but his actual final stuff is in codimension 1. It's for the 3-sphere. In about 2015 or so, Sheikh and Daye and Rainer Schätzle did a very elaborate calculation that actually Peng Wang and I did together independently, but I guess later we didn't know that they had done this. But in between, there's this sort of nice kind of variational approach to doing it, which I think people should know better. It's sort of a there. So this was from the 1980s, and I guess it was 2017 that Peng Wang and yours truly sort of redid various versions of that. So it should be better understood. I hope it will be. Okay, so what about some examples here? So just quickly, so this is the domain of the. So if I put this into S3 or Sn, okay. This is the Clifford torus, this white guy here, namely putting it inside as a circle of length root 2 pi, or radius 1 over root 2. So this is the Clifford, square Clifford torus, which is minimal. And you can quickly analyze, so what's L on here? So L is just the flat Euclidean Laplacian plus, well, there's the 2 from the Ricci term, and there's a 2 because it has constant length second fundamental form, also of length 2, so it's Laplacian plus 4. And so the spectrum there, if I were to draw the picture of the alpha spectrum, right? So I get, of course, 0 is in there, and -2 is in there. And then the base of the spectrum is actually, for the constants, is at -4. Okay? So -4, -2, excuse me. Okay, so this is the eigenvalue 1. There's a 4-parameter family of things there, and this actually reflects the fact the index, the area index, right? The area index of Clifford is 5, right? And there's nothing else there, and then it heads up. Okay. I think the next eigenvalue is 2 actually, and that's well, actually I'm not gonna, I didn't write it down, so I don't know. Anyway, these actually correspond also to the, so they correspond either to the coordinate functions, which are eigenvalues of the Laplacian with eigenvalue 2, or to the normal components, because the normal components gives the coordinates of the polar surface, the surface that you get by going along the normal pi/2 distance from the surface. So these are either, think of them as coordinate functions or the coordinates of the normal. The polar of the Clifford torus it's sort of itself rotated. So, and this is the constant. function. So this is the multiplicity I'm writing here, but it's also the constant function 1, okay? So another surface that's sort of interesting, and again, I leave you now to play with this. You need to use first year PD separation of variables, I guess, to do this, but there's a double cover of the Clifford torus, okay? It's not embedded surface, it's an immersed surface. It's actually the other regular homotopy class. Franz showed some pictures of this, those classes. I don't think he actually drew this one because it looks just like the Clifford torus. It's just it's got two sheets instead of one, but it's important that you double cover it diagonally, okay? So there are really several different double covers. There are ones you could go the long way. Those introduce eigenvalues that appear in the gap, okay? If you go the long way this way or this way. But if you do this diagonal double cover, lo and behold, I mean, I'll let you do it. I'm running out of time. No eigenvalues appear there. So the double cover, this guy here, the diagonally double covered, this is the non-embeddable one. It's the one corresponding to, well, no, the other ones are regular homotopic to an embedding. So this is the one, I don't know if Franz said it this way, but you're going to associate the spin structure to a certain class of holomorphic differentials with even order zeros and poles. This is the one that's like DZ. This is the one without anything. The other ones have pole. It's funny. The twisted one is the one with the simplest. It's a correction of what you actually had. This is the one that, think about it. Yeah. So this is the spin structure that's both bands are twisted. Yeah. So if you want to think of, I don't, again, let me someone said, John, was it you who said I was known as more as a topologist at the beginning when we were introducing ourselves? Someone said that to me. You said, Eric said that, okay. Yeah, so let me play topologist for a minute. So a torus is a disk with two bands attached, two untwisted bands attached, intrinsically untwisted, not half twisted. And they're attached in a plumb together way. So this is me getting to be topologist for a minute. So it's this picture. The picture goes back to Möbius, actually, to Möbius. So here's one band attached, and then here's the other band attached. So you all know that picture, I'm sure. Okay. And if you put a full twist in one of the bands, that's actually regularly homotopic to an embedding, okay? Okay. So if I put a full twist, and you can see that in some ways by sliding the band over the other band. It's a low-dimensional topology. If you put twists in both the bands, then when you do that, it still remains twisted. That's one way to at least convince yourself that this is, so if I put a full twist in each of these, so however I should draw that, here. And the same thing there. That's the regular homotopy class. Okay? That diagonally double covered embedded torus is actually a twisted torus in the sense that it's not regular homotopy to embedding. So this diagonally double covered thing is also W stable. In fact, I'll conjecture this here for the first time, now maybe, again, 30 years ago, 35 years ago. This is probably the minimizer in the regular homotopy class. Now that we know the solution to the Willmore conjecture, what else could it be? Somebody should prove that before Friday. I leave at noon on Friday, so I want to see the proof of that. I won't even ask to be a co-author. Okay, but I can't believe that we don't know the answer to that. But actually, maybe if I get to this, I'll point out something that Peng mentioned yesterday to me, which is that this doesn't persist. So let me now turn to the first sort of theorem. So this, in some sense, this stuff here is fairly elementary. It goes back to at least Joel Weiner and some calculations that I played with in the 80s, and that other people like Peng and I have rediscovered other ways of doing it in the last few years. And I think more people should study it. I mean, Peng and I spent the last couple of days trying to use this to prove something that we really want to prove, but I'll get to that in a minute. So let's see. So let me state the first theorem. So there's I have these two spectra here. So there's an interesting connection with one more with one more operator. Okay. And that's the Laplacian itself, okay? So how about the Laplacian? So what's the spectrum of the Laplacian on here? So what's the spectrum of the Laplacian on a minimal surface? So there's one element in it, namely 2, because remember, minimal, I didn't write this, but the minimal surface, right, if I write down the position function, so the embedding, I think of x as the embedding of sigma into Sn, then if you take that picture and move the mean curvature of the surface, that h without the bar, to be 0, then that's equivalent to the statement that Laplacian plus 2x, Laplacian of x plus 2x is 0. So in other words, the coordinate functions, x1 up to xn plus 1, these are all eigenfunctions of the Laplacian with eigenvalue 2. Okay? Notice where side my eigenvalue appears on. Okay, so the is it -2 or +2? I think if I have it set up, it's 2. If I haven't screwed up too much here, because my L here is well, I don't know. There's some minus signs messing up. So that's there. And so one question that's been around for since 1979. I was reading Yao's book, The Shape of a Life. Very interesting book. I recommend it to you, but be prepared to not like it. Anyway, it's a very strange book, but it's very interesting also. So Yao conjectured in the late 1970s that every embedded minimal surface in the n-sphere should be every embedded minimal hypersurface in the n-sphere should have its lowest, so it should be embedded by its first non-trivial eigenfunction, which would be, so for a hypersurface, this 2 would be, so this is sigma 2. For a hypersurface, this would be n-1 for a hypersurface. Okay, so Yao's conjecture was for hypersurface, embedded minimal hypersurfaces, and so 2 is always, whatever the codimension, 2 is always an eigen, so 2 is always in there. And the question is, for a hypersurface, so Yao's conjecture, okay, is that if I have a minimal hypersurface embedded in n-1 embedded in Sn, that lambda 1 of the Laplacian, the first eigenfunction of eigenvalue of the Laplacian, should be n-1. Okay, and so in particular, when I have a surface in S3, we expect lambda 1 equal to 2. In other words, okay. And you can check that corresponds to this picture here. Okay. So just by the way, since you asked about this, the shift by 4 here, what this means is that the Laplacian spectrum is shifted up by 4. That's where the minus sign, in case you're keeping track of signs. Okay. This is the spectrum of this guy. If I shift up, if I add the 4, it shifts the spectrum up by 4 in this direction. The -4 becomes 0, that's the constants. The -2, the coordinate functions become 2, and so forth, just to keep track of the signs there. Okay, so suppose you have a minimal surface, two-dimensional minimal surface, maybe an Sn, that satisfies Yao's conjecture. That has lambda 1 equals 2. Well, there's an interesting feature that Peng and I discovered. So it's basically a relationship between the spectrum of this guy and, if you like, the spectrum of these other two operators, L and J. Okay, so this is. This is from about 2 years ago now. We haven't put it on the archive yet. We have a paper, but we have to get it in good shape. So suppose lambda 1 of sigma. So sigma is minimal in Sn, two-dimensional minimal surface. Suppose this is true, then so under this condition, so here's the theorem. It says that if well, let me write this if and only if statement. Sigma is W stable how should I write this? Yes, it's W, yeah.
Suppose lambda 1 sigma equals, is this a complete sentence or is it?
Thank you. I think I said it but didn't write it. Okay, thank you. Suppose, so this is W stable in Sn if and only if it's W stable. So now I have to, let me explain. I want to think of this as, so there's a standard embedding of Sn in Sn plus 1 and so forth, okay, by just putting it totally geodesically. And I'm going to put this in okay, so we call this persistent. A little more stability. Maybe I should write this differently. Also, I think there's a bunch of if and only ifs. Actually, let me write it this way. This is the inequality. It's this way. Peng's going to correct me. This is what's true. Okay. That's the right statement. Lambda 1 is 2. The lambda 1 of lambda 1 of sigma is 2 if and only if you start with something Willmore stable in Sn, that it remains Willmore stable. Okay? Okay, so the idea is actually kind of simple. Okay? And it's to look at the this operator here, and think about what A, this operator A does, okay, when you take a variation, okay. So how does that operator A, so it's basically the second fundamental form acting on your variation. Okay. Well, I can give you the microphone. If you take a variation that's in Sn, so that pushes in the Sn, a normal section that actually sits inside the tangent bundle to Sn, then we know it's Willmore stable. But if you go up to one higher codimension, namely in Sn plus 1, by taking a variation along the say the normal to the embedding of Sn in Sn plus 1, well, that normal is a parallel field, okay, on the surface, and it's also it gives you 0 when you apply the A operator to it, because it's totally geodesic. That's a totally geodesic embedding. So what you find is that if you write, so the idea behind this is you take your extra variation, so some extra variation, and write it as a function, say g times the normal, where n is the normal section, so normal section to and then when you apply L to that, what you see is that L of V is basically just the Laplacian on functions, because it's a parallel section. Well, G plus 2G. And now you just play off. If you've got an eigenvalue for the Laplacian that's less than 2, Okay, if this is, so so if the first eigenvalue is 2, then basically you don't get any new spectrum between -2 and 0. I'm not making this very clear, but it's just, and if you do have an eigenvalue less than 2, then you plug in the corresponding eigenfunction and you get an eigenvalue that lies in the interval, in this interval. Okay, so that's the idea behind that. So simply to look at the behavior of this operator on this very simple test section. Okay. So let's take a look at this example here. Okay. Okay. So the Willmore stability of this diagonally double covered surface I've left as an exercise for you, but what happens to lambda 1 of the Laplacian for this? Okay. I mean, this guy here, the Clifford torus, you can check, is got lambda 1 equals 2. This is a square torus also. It's just something intrinsic. You do this just looking at the square itself. I've doubled the area of the square. The first eigenvalue drops like 1 over the area. So this is a lambda 1 of this guy. Lambda 1 is just 1 for that one. So what does that mean? That means that the diagonally double covered Clifford torus, it's Willmore, so the corollary of this is that it's this diagonally double covered guy. This is in W stable in S3, but not in S4 and on up. Okay, so it stops being stable. Somehow it could be unwrapped. On the other hand, the Clifford torus remains Willmore stable all the way up. So it's the Clifford torus we know is the minimizer in S3 for Willmore functional, but actually is locally the minimizer all the way up for all codimension.
Also, of course, in S4 this has normal bundle 0 still.
It's a trivial normal bundle.
So that's the only constraint you have there of homotopy. So you can completely undo it.
Yeah. So Franz's point is that it can be regularly homotope to an embedding now. And so I guess it's quite reasonable, but here's a proof that that's actually unstable. Okay, I have 5 minutes plus whatever amount of time you wanted to grant me. So give me, just tell me, because he's gonna hold that. So he's holding 10 minutes. And I remember someone, where's Davi? Davi? Yeah. I remember your 5 minutes went about an hour. So I'll try to not take too much longer this. I could tell you lots more stuff, but see, the agreement Peng and I had, and he's smiling, is that, see, he's talking tomorrow. You should all come to his talk, because he promised that everything I don't say, he's gonna make correct or fill in, right? Right? And he's smiling. Now he's denying that, but so let's see. So what else do I want to tell you? A couple more things. So let me take a few minutes and tell you about the other main thing that Peng and I have worked out. And again, I want to just sort of sketch this. So let's see. So one of the questions so this was the genus 1 case. You're going to say a lot about genus 1 stuff tomorrow about the index characterization of minimal tori and so on. I want to let me show one other torus, but maybe Peng will say more about this too. So here's another torus. So Franz knows this one because it was his birthday torus. So this that's a torus. Can you see the torus there? Okay, so that Clifford torus you can think of as the maximal torus in U2, I guess. So this is a picture of the maximal torus in U3. This big thing here. So this guy here, this is a 3 torus, S1 cross S1 cross S1. This big guy here, Gesundheit, sitting in S5, which I'll think of as, say, C3. And it's the maximal torus of U3, if you like. It's a cubic torus. But inside there is this beautiful hexagonal torus. Well, there's the hexagon, but there's 2 more parts, which is the maximal torus of, so this, if you like, you can sort of think of this morally as the maximal torus of, U3, but sitting inside there is the maximal torus of SU3, which is if you like, a trace condition. It's sort of a linearized picture of it. And the trace condition tells you that you're either on the plane perpendicular to the 1, 1, 1 direction, or with passing through the origin, or you're on the plane passing through sort of a 2/3 of the way this way or this way. Again, this is an exercise in your Lie theory class, okay, but very elementary exercise. But this is a picture of the torus that's I guess was first discovered by well, I don't know who first discovered it. Ito maybe. So a long time ago, and it was studied by Robert Bryant and by Ahmed Al-Sufi, who I actually wanted to say I'm a very good friend of mine. I think I met him first when I visited Martin and Marc in Tours, and I was sorry to hear that he's no longer with us, and sort of dedicated to him in some sense, this torus. So he and Said Elias studied this, as did Montil and Ross. And this torus has it's the only other torus that's actually embedded with lambda 1 = 2, this hexagonal torus. So lambda 1 of this T2 hex that goes back to Ito. Okay, so we call it the Ito Bryant Montil Ross torus, something like that. This is also has eigenvalue 2. And it turns out that it's stable. So the spectrum of this torus is actually quite interesting. I won't try to draw it, but it has it also has obviously these two as eigenvalues for the spectrum of the Jacobi operator. The Jacobi operator is a little more complicated. It turns out they're two exotic eigenfunctions of the Jacobi operator. The Jacobi operator is now this operator that has a not a scalar value, but a symmetric endomorphism value, a potential term there. But it turns out that the other two exotic eigensections could be thought of in a very nice geometric way. Namely, you think of this hexagonal torus. So do you see the torus? Maybe Peng will draw a better picture. But if you translate this thing up, this guy in the back, and translate this down, for example, then you get the rhombus, the hexagonal rhombus, and that's the torus. So you can either see it sitting inside the cube, or by identification, I can think of it as this rhombus. Okay, so that's the equilateral torus sitting in there, and the variation, the two extra variations, come from moving this minimal 3. This is a 3 torus, right? It's a Clifford. This is a 2 torus. It's a Clifford 3 torus inside the 5 sphere. And what you do is you move it through what you might call parallel tori, i.e. you change the radii of the circles. So the radii of each of the circles are, of course, √3/3. You change those radii, and the constraint of being on the sphere gives you one constraint. And so that gives a 2-parameter family. And those variations, they're very geometric, but they're not coming from ambient conformal motions. They turn out to also be in the eigenspace -2. In other words, they're in the kernel of this Willmore Jacobi operator. Okay, so it's got extra kernel there, but there's nothing else in there. So this is also W stable. So this guy is also W stable in S5. Okay, and by this persistence theorem, it remains W stable all the way up. But the big surprise, which I don't know if you'll talk about it, and I won't have time to talk about it, is that it turns out that it's not a minimizer. In fact, if I take those two variations, and you can almost do it by synthetic geometry. Okay, if I take the variations, these two exotic variations, the third derivative, okay, it's not an umlaut, it's a 3 dots. Third derivative along these exotic guys is non-zero. It's a non-zero third variation. And because it's an odd variation, that means that if I go one way, we go one way, then we get something that's got less Willmore energy. So but not a W minimizer. And this is the reason, okay? Okay, so this suggests at least that something that we expect, although we don't know how to prove it, that the Willmore minimizer among tori for every codimension is still the Clifford torus. This would be the only other possible example, because none of the other tori are persistently stable. But this is a theorem of, I guess, Montil and Ross, that the Clifford torus and this torus are the only two tori with lambda 1 equal to 2. Yeah. And El Sufi and Elias also did that, yeah. Or did they do? I see, okay. Well, I thought Montil Ross also did this example, though. This example, too. Yeah, okay, thank you, that's good. So I don't know if that's a conjecture or not to put for the ages, but I think we say that basically the only two, it's evidence that some evidence that the only, well, so let me say it clearly, the only persistently stable tori are these guys, and so that means eventually all the other tori become unstable. And so it's some evidence for the conjecture that the Clifford torus in S3 is the only minimizer in any codimension as well among tori for the Willmore functional. Okay, so I don't know. I have 5 more minutes. Now it says 1 more minute. So I can do arithmetic. Okay. Oh, maybe I see. Okay. So let me close this with one other thing, which is what about higher genus? Okay, so we heard a lot about, in Martin Trezet's talk, we saw pictures of the Lawson. So for higher genus, we have these so-called Lawson surfaces, so Lawson surfaces. And you've seen pictures of those, I hope, in the talk. So the Lawson surfaces, by results of Mark and Jae-Gyung Cho, okay, these guys also have lambda 1 equal to 2. They're embedded by their first eigenfunctions. In fact, all the Lawson surfaces, all the minimal surfaces we know actually have this property, and Mark and Jae-Gyung gave a really nice geometric proof of this. So the other theorem that Peng and I have proven is a complement to this theorem. Okay, it actually uses the very same proof in some sense, which is that we can not only evaluate the eigenfunction, but the multiplicity. Let me call that M1. Okay, so M1 of sigma. Okay, of all the Lawson surfaces, in fact, all the surfaces that you guys prove have lambda 1 equal to 2, the multiplicity is of that eigenfunction. So this is the multiplicity of that eigenfunction. Multiplicity of the first eigenfunction. And that has, so it uses the same, if you like, reasoning. If it had multiplicity higher than 4, then we would cook up, we could find a function that was orthogonal to it and blah, 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 and decide that it's 0. Okay, so that's quickly. But one of the consequences of this, so a corollary of this is rather interesting. It says that all these surfaces, in particular so in fact all Lawson surfaces, so, or in general C and K, okay, all these minimal surfaces, I guess we know from Montil and Ross and a little bit of argument using conformal area that they would be candidates for being the Willmore minimizers in the conformal class, but they are uniquely minimizing, unique up to Möbius transformation, of course. Minimizers, W minimizers, intrinsic, so Riemann surface, if you like, conformal class. Okay, and that uses the fact that since the multiplicity is 4, any other way you can put it into the sphere, actually the minimal surface, it has to be a rotation of the sphere. And then a little more argument says that if I allow, if I'm just looking at them as Willmore surfaces, then you can allow the Möbius transformations. And sort of a meta-corollary to that is sort of amusing. If I take the higher ones here, if the genus is a composite number, you could take different values of m and k and still get the same genus. So the genus of this guy, is of CMK is the product of these guys. So for example, if m were, I don't know, give me a number. What's the first good composite number? 6? Good one. Well, even 4, I guess, works nicely, right? So, yeah, so C41 and C22. I don't know if we can actually prove it for these. So these are 2 examples with genus 4, okay? Well, these guys can't be, well, they shouldn't be conformally equivalent to each other. So in general, if I look at their conformal classes, these aren't the same, okay? Because they have different area. And I'll stop there. Thank you.
All right, thank you very much. Thank you for a very interesting talk. Is this switched on? Do we have any questions or comments, please? So, Frank seems to be full of private comments. Do you have a public one?
Intrinsic Riemann surface structure. I mean, sort of the symmetries these surfaces have are sort of characterizing them. So, how could a Riemann surface with the 4-1 symmetry be conformal to the 2-2 symmetry?
So
independently of this.
So let me ask you. So we know there are techniques to do this.
That's a question.
Yeah, no, I understand. So I first of all, I agree that there should be a way to see it just from the symmetry groups. But how do you tell whether if you know your Hurwitz, there's a famous Hurwitz upper bound on the order of the conformal automorphisms. If you could show that those groups are distinct, then you're right, you'd have another proof of that. I don't know how to prove that there are no other conformal symmetries. So I mean, I agree with the spirit of your comment, but this is one way. As soon as you know their areas are different, you know they can't be the same, because there's a unique minimizer for the area. By the way, is the Willmore energy for the minimal surface. I didn't say it, but it's obvious. So it's a curious intrinsic corollary from conformal area.
Okay, thanks very much. Any more questions or comments? I'd just like to say you must have computed the third variation. You were telling us all to do it, and you've done it, right? Oh, right. Okay.
Well, so let me tell you. So there are 2 ways it was done. One was an amazing, insanely difficult calculation, but the other is to now just do what I indicated, namely take variations of that cube through rectangular boxes that satisfy the constraint of having some of the square lengths being 1. You can then compute by calculus the third variation, and it's non-zero. Third derivative. It's a calculus problem. Yeah, Peng has a comment.
There's another way to show that is Willmore not Willmore mean measure, is that in Montiel-Rose's paper they have a series of torus. The Willmore energy is computed in Robert Brandt's paper. You just compute the third derivatives. You show that the Willmore energy, the W3 dot is not 0. So
Yeah,
we will
it's-
show that.
It's implicit there. It's not
Yeah, they
very.
have the formula. You just do.
Yeah.
It's like an exercise for calculus, really calculus. Yeah. And also there's another remark is that it's constrained Willmore minimizer. That torus.
Yeah. So in its whatever hexagonal conformal class, it's the minimizer for that.